Electrostatic potential and capacitance. Introduction. When an external force does work in taking a body from a point to another against a force like spring force or gravitational force, that work gets stored as potential energy of the body. When the external force is removed, the body moves, gaining kinetic energy and losing an equal amount of potential energy. The sum of kinetic and potential energies is thus conserved. Forces of this kind are called conservative forces. Examples: spring force and gravitational force. Coulomb force between two stationary charges is also a conservative force, since both have inverse square dependence on distance and differ mainly in the proportionality constants. The masses in the gravitational law are replaced by charges in Coulomb's law. Thus, like the potential energy of a mass in a gravitational field, we can define electrostatic potential energy of a charge in an electrostatic field. Consider an electrostatic field E due to some charge configuration. First, for simplicity, consider the field E due to a charge Q placed at the origin. Now, imagine that we bring a test charge Q from a point R to a point P against the repulsive force on it due to the charge Q with reference. To figure 2.1, this will happen if Q and Q are both positive or both negative. For definiteness, let us take Q greater than 0. Two remarks may be made here. First, we assume that the test charge Q is so small that it does not disturb the original configuration, namely the charge Q at the origin. Second, in bringing the charge Q from R to P, we apply an external force F external just enough to counter the repulsive electric force Fe, that is F external equals minus Fe. This means there is no net force on or acceleration of the charge Q when it is brought from R to P, that means it is brought with infinitesimally slow constant speed. In this situation, work done by the external force is the negative of the work done by the electric force, and gets fully stored in the form of potential energy of the charge Q. If the external force is removed on reaching P, the electric force will take the charge away from Q. The stored energy, potential energy, at P is used to provide kinetic energy to the charge Q in such a way that the sum of the kinetic and potential energies is conserved. Thus, work done by external forces in moving a charge Q from R to P is given by the equation 2.1. This work done is against electrostatic repulsive force and gets stored as potential energy. At every point in electric field, a particle with charge Q possesses a certain electrostatic potential energy. This work done increases its potential energy by an amount equal to potential energy difference between points R and P. Thus, potential energy difference is given by the equation 2.2. Therefore, we can define electric potential energy difference between 2 points as the work required to be done by an external force in moving, without accelerating, charge Q from one point to another for electric field of any arbitrary charge configuration. Two important comments may be made at this stage. 1. The right side of equation 2.2 depends only on the initial and final positions of the charge. It means that the work done by an electrostatic field in moving a charge from one point to another depends only on the initial and the final points and is independent of the path taken to go from one point to the other. This is the fundamental characteristic of a conservative force. The second comment is equation 2.2 defines potential energy difference in terms of work. We can always add an arbitrary constant alpha to potential energy at every point, since this will not change the potential energy difference. UP plus alpha minus UR plus alpha is equal to UP minus UR. Put it differently, there is a freedom in choosing the point where potential energy is 0. A convenient choice is to have electrostatic potential energy 0 at infinity. With this choice, if we take the point R at infinity, we get from equation 2.2, W infinity P equals UP minus U infinity equals UP, 2.3. Since the point P is arbitrary, equation 2.3 provides us with a definition of potential energy of a charge Q at any point. Potential energy of charge Q at a point is the work done by the external force in bringing the charge Q from infinity to that point. Electrostatic potential. Consider any general static charge configuration. We define potential energy of a test charge Q in terms of the work done on the charge Q. This work is proportional to Q, since the force at any point is QE, where E is the electric field at that point due to the given charge configuration. It is, therefore, convenient to divide the work by the amount of charge Q, so that the resulting quantity is independent of Q. In other words, work done per unit test charge is characteristic of the electric field associated with the charge configuration. This leads to the idea of electrostatic potential V due to a given charge configuration. From equation 2.1, we get work done by external force in bringing a unit positive charge from point R to P is given by the equation 2.4, where Vp and Vr are the electrostatic potentials at P and R, respectively. If we choose the potential to be 0 at infinity, equation 2.4 implies work done by an external force in bringing a unit positive charge from infinity to a point equals electrostatic potential, V, at that point. In other words, the electrostatic potential, V, at any point in a region with electrostatic field is the work done in bringing a unit positive charge, without acceleration, from infinity to that point. To obtain the work done per unit test charge, we should take an infinitesimal test charge delta Q, obtain the work done delta W in bringing it from infinity to the point, and determine the ratio delta W by delta Q. Also, the external force at every point of the path is to be equal and opposite to the electrostatic force on the test charge at that point. Potential due to a point charge. Consider a point charge Q at the origin, figure 2.3. For definiteness, take Q to be positive. We wish to determine the potential at any point P with position vector r from the origin. For that we must calculate the work done in bringing a unit positive test charge from infinity to the point P for Q greater than 0. The work done against the repulsive force on the test charge is positive. Since work done is independent of the path, we choose a convenient path, along the radial direction from infinity to the point P. At some intermediate point P' on the path, the electrostatic force on a unit positive charge is given by the equation 2.5. Where r' is the unit vector along op'. Work done against this force from r' to r' plus delta r' is given by equation 2.6. The negative sign appears because for delta r' less than 0, delta W is positive. Total work done, W, by the external force is obtained by integrating equation 2.6 from r' equals infinity to r' equals r, is given by the equation 2.7. This, by definition, is the potential at P due to the charge Q and is given by the equation 2.8. Equation 2.8 is true for any sign of the charge Q, though we consider Q greater than 0 in its derivation. For Q less than 0, V less than 0, which means work done by the external force per unit positive test charge in bringing it from infinity to the point is negative. Finally, we note that equation 2.8 is consistent with the choice that potential at infinity be 0. Figure 2.4 shows how the electrostatic potential, directly proportional to 1, r, and the electrostatic field, directly proportional to 1, r square, varies with r. Potential due to an electric dipole. An electric dipole consists of two charges Q and Q separated by a small distance 2a. Its total charge is 0. It is characterized by a dipole moment vector P whose magnitude is Q times 2a and which points in the direction from minus Q to Q, figure 2.5. We also saw that the electric field of a dipole at a point with position vector r depends not just on the magnitude r, but also on the angle between r and P. Further, the field falls off, at large distance, not as 1 by r square, typical of field due to a single charge, but as 1 by r cube. We, now, determine the electric potential due to a dipole and contrast it with the potential due to a single charge. As before, we take the origin at the center of the dipole. Now we know that the electric field obeys the superposition principle. Since potential is related to the work done by the field, electrostatic potential also follows the superposition principle. Thus, the potential due to the dipole is the sum of potentials due to the charges Q and minus Q. That is given by the equation 2.9, where r and r are the distances of the point P from Q and minus Q, respectively. Now, by geometry, we get the expressions for r1 square and r2 square. We take r much greater than r and retain terms only up to the first order in a by r, we get the equations 2.11 and 2.12. Using the binomial theorem and retaining terms up to the first order in a, r, we obtain the equations for 1 by r1 and 1 by r2. Using equations 2.9 and 2.13 and P equals 2qa, we get the equation 2.14. Now, P cos theta equals P dot r, where r cap is the unit vector along the position vector op. The electric potential of a dipole is then given by the equation 2.15. Equation 2.15 is approximately true only for distances large compared to the size of the dipole, so the higher order terms in a by R are negligible. For a point dipole P at the origin, equation 2.15 is, however, exact. From equation 2.15, potential on the dipole axis, theta equals 0, pi, is given by the equation 2.16. Positive sign for theta equals 0, negative sign for theta equals pi. The potential in the equatorial plane, theta equals pi by 2, is 0. The important contrasting features of electric potential of a dipole from that due to a single charge are clear from equations 2.8 and 2.15. The potential due to a dipole depends not just on r but also on the angle between the position vector r and the dipole moment vector p. The electric dipole potential falls off, at large distance, as 1 by r square characteristic of the potential due to a single charge. Potential due to a system of charges. Consider a system of charges q1, q2, qn with position vectors r1, r2, rn relative to some origin, figure 2.6. The potential V1 at P due to the charge q1 is given by the following equation. Where r1p is the distance between q1 and P. Similarly, the potential V2 at P due to q2 and V3 due to q3 are given by the following equation. Where r2p and r3p are the distances of P from charges q2 and q3, respectively, and so on for the potential due to other charges. By the superposition principle, the potential V at P due to the total charge configuration is the algebraic sum of the potentials due to the individual charges. V equals V1 plus V2 plus Vn. The potential V at P is given by the following equation 2.18. If we have a continuous charge distribution characterized by a charge density ρ r, we divide it into small volume elements each of size delta V and carrying a charge ρ delta versus. We then determine the potential due to each volume element and sum over all such contributions, and thus determine the potential due to the entire distribution. We have seen in Chapter 1 that for a uniformly charged spherical shell, the electric field outside the shell is as if the entire charge is concentrated at the center. Thus, the potential outside the shell is given by the equation 2.19, where Q is the total charge on the shell and r its radius. The electric field inside the shell is 0. This implies that potential is constant inside the shell, as no work is done in moving a charge inside the shell, and, therefore, equals its value at the surface, which is given by the equation 2.19b. Equipotential surfaces. An equipotential surface is a surface with a constant value of potential at all points on the surface. For a single charge q, the potential is given by equation 2.8. This shows that V is a constant if r is constant. Thus, equipotential surfaces of a single point charge are concentric spherical surfaces centered at the charge. Now the electric field lines for a single charge q are radial lines starting from or ending at the charge, depending on whether q is positive or negative. Clearly, the electric field at every point is normal to the equipotential surface passing through that point. This is true in general. For any charge configuration, equipotential surface through a point is normal to the electric field at that point. The proof of this statement is simple. If the field were not normal to the equipotential surface, it would have non-zero component along the surface. To move a unit test charge against the direction of the component of the field, work would have to be done. But this is in contradiction to the definition of an equipotential surface. There is no potential difference between any 2 points on the surface and no work is required to move a test charge on the surface. The electric field must be normal to the equipotential surface at every point. Equipotential surfaces offer an alternative visual picture in addition to the picture of electric field lines around a charge configuration. For a uniform electric field E, say, along the x-axis, the equipotential surfaces are planes normal to the x-axis, i.e., planes parallel to the yz plane, figure 2.10. Equipotential surfaces for A dipole and B, two identical positive charges are shown in figure 2.11. Relation between field and potential. Consider two closely spaced equipotential surfaces A and B, figure 2.12, with potential values V and V plus delta 5, where delta 5 is the change in V in the direction of the electric field E. Let P be a point on the surface B. Delta L is the perpendicular distance of the surface A from P. Imagine that the unit positive charge is moved along this perpendicular from the surface B to surface A against the electric field. The work done in this process is E. Delta L. This work equals the potential difference VA minus VB. Thus, E. Delta L equals V minus V plus delta 5 equals minus delta 5. So the electric field is given by the equation 2.20. Since delta 5 is negative, delta 5 equals minus delta 5, we can rewrite equation 2.20 as equation 2.21. We thus arrive at two important conclusions concerning the relation between electric field and potential. Electric field is in the direction in which the potential decreases steepest. Its magnitude is given by the change in the magnitude of potential per unit displacement normal to the equipotential surface at the point. Potential energy of a system of charges. Consider first the simple case of two charges Q1 and Q2 with position vector R1 and R2 relative to some origin. Let us calculate the work done, externally, in building up this configuration. This means that we consider the charges Q1 and Q2 initially at infinity and determine the work done by an external agency to bring the charges to the given locations. Suppose, first the charge Q1 is brought from infinity to the point R1. There is no external field against which work needs to be done, so work done in bringing Q1 from infinity to R1 is 0. This charge produces a potential in space given by V1, where R1P is the distance of a point P in space from the location of Q1. From the definition of potential, work done in bringing charge Q2 from infinity to the point R2 is Q2 times the potential at R2 due to Q1. Work done on Q2 is given below.
Where R12 is the distance between the points 1 and 2. Since electrostatic force is conservative, this work gets stored in the form of potential energy of the system. Thus, the potential energy of a system of two charges Q1 and Q2 is given by the equation 2.22, that is U is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. Obviously, if Q2 was got first to its present location and Q1 got later, the potential energy U would be the same. More generally, the potential energy expression equation 2.22 is unaltered whatever way the charges are brought to the specified locations because of path independence of work for electrostatic force. Equation 2.22 is true for any sign of Q1 and Q2. If Q1 Q2 is greater than 0, potential energy is positive. This is as expected since for like charges Q1 Q2 is greater than 0. Electrostatic force is repulsive and a positive amount of work is needed to be done against this force to bring the charges from infinity to a finite distance apart. For unlike charges, Q1 Q2 is less than 0, the electrostatic force is attractive. In that case, a positive amount of work is needed against this force to take the charges from the given location to infinity. In other words, a negative amount of work is needed for the reverse path from infinity to the present location. So the potential energy is negative. Equation 2.22 is easily generalized for a system of any number of point charges. Let us calculate the potential energy of a system of three charges Q1, Q2 and Q3 located at R1, R2 and R3 respectively. To bring Q1 first from infinity to R1, no work is required. Next, we bring Q2 from infinity to R2. As before, work done in this step is Q2 V1 R2 is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. The charges Q1 and Q2 produce a potential which at any point P is given by V12 is equal to 1 by 4 pi epsilon naught Q1 by R1P plus Q2 by R2P. Work done next in bringing Q3 from infinity to the point R3 is Q3 times V12 at R3. Q3 V12 R3 is equal to 1 by 4 pi epsilon naught Q1 Q3 by R13 plus Q2 Q3 by R23. The total work done in assembling the charges at the given locations is obtained by adding the work done in different steps. That is equation 2.23 and equation 2.25. So U is given by 1 by 4 pi epsilon Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. Again, because of the conservative nature of the electrostatic force or equivalently the path independence of work done, the final expression for U, that is the equation 2.26, is independent of the manner in which the configuration is assembled.
Is characteristic of the present state of configuration, and not the way the state is achieved. Potential energy in an external field. Potential energy of a single charge. What is the potential energy of a charge Q in a given field? This question was, in fact, the starting point that led us to the notion of the electrostatic potential, sections 2.1 and 2.2. We are now concerned with the potential energy of a charge, or charges, in an external field. The external field E is not produced by the given charges whose potential energy we wish to calculate. E is produced by sources external to the given charges. The external sources may be known, but often they are unknown or unspecified. What is specified is the electric field E or the electrostatic potential V due to the external sources. We assume that the charge Q does not significantly affect the sources producing the external field. This is true if Q is very small, or the external sources are held fixed by other unspecified forces. Even if Q is finite, its influence on the external sources may still be ignored in the situation when very strong sources far away at infinity produce a finite field E in the region of interest. The external electric field E and the corresponding external potential V may vary from point to point. By definition, V at a point P is the work done in bringing a unit positive charge from infinity to the point P.
We continue to take potential at infinity to be 0. Thus, work done in bringing a charge Q from infinity to the point P in the external field is QV. This work is stored in the form of potential energy of Q. If the point P has position vector R related to some origin, we can write potential energy of Q at R in an external field is equal to Q into VR, where VR is the external potential at the point R. Thus, if an electron with charge Q is equal to E equal to 1.6 in 10 power minus 19 coulomb, is accelerated by a potential difference of delta V, which is given by 1 volt. It would gain energy of Q into delta V, that is equal to 1.6 into 10 power minus 19 joule. This unit of energy is defined as 1 electron volt or 1 eV, that is 1 electron volt is equal to 1.6 into 10 power minus 19 joule. The units based on electron volt are most commonly used in atomic, nuclear and particle physics, where 1 kilo electron volt equal to 10 power 3 electron volt, that is equal to 1.6 in 10 power minus 16 joule. And 1 million electron volt is equal to 10 power 6 electron volt, that's equal to 1.6 10 power minus 13 joule. And 1 giga electron volt is given by 10 power 9 electron volt, that's given by 1.6 10 power minus 10 joule. And 1 tera electron volt, that's given by 10 power 12 electron volt, that's equal to 1.6 10 power minus 7 joule. Next topic is given by the potential energy of a system of two charges in an external field. Next, we ask what is the potential energy of a system of two charges Q1 and Q2 located R1 and R2 respectively in an external field. First, we calculate the work done in bringing the charge Q1 from infinity to R1. Work done in this step is Q1 VR1 using the equation 2.27. Next, we consider the work done in bringing Q2 to R2. In this step, work is done not only against the external field E, but also against the field due to Q1. So the work done on Q2 against the external field is given by Q2 into VR2. Work done on Q2 against the field due to Q1 is given by Q1 Q2 by 4 pi epsilon naught R12, where R12 is the distance between Q1 and Q2. We have made use of the equations 2.27 and 2.22. By the superposition principle for fields, we add up the work done on Q2 against the two fields, E and that due to Q1. So the work done in bringing Q2 to R2 is given by Q2 V of R2 plus Q1 Q2 by 4 pi epsilon naught R12, that is given by the equation 2.28. Thus, the potential energy of the system is given by the total work done in assembling the configuration, and that is given by Q1 V of R1 plus Q2 V of R2 plus Q1 Q2 by 4 pi epsilon naught R12, that's given by the equation 2.29. Potential energy of a dipole in an external field. Consider a dipole with charges Q1 equal to first Q In Q equal to minus Q, placed in a uniform electric field E, as shown in the figure 2.16. As seen in the last chapter, in a uniform electric field, the dipole experiences no net force, but experiences a torque tau, which is given by tau equal to P cross E, which will tend to rotate it unless P is parallel or anti-parallel to E. Suppose an external torque tau is applied in such a manner that it just neutralizes this torque and rotates it in the plane of paper from angle theta 0 to theta 1 at an infinitesimal angular speed and without angular acceleration. The amount of work done by this one torque will be given by W equal to integration of theta 0 to theta 1 P extern of theta d theta, that is given by integral theta 0 to theta 1 P sin theta d theta, that is given by P cos theta 0 minus cos theta 1. This work is stored as potential energy of the system. We can then associate potential energy U theta with an inclination theta of the dipole. Similar to other potential energies, there is a freedom in choosing the angle where the potential energy U is taken to be 0. A natural choice is to take theta 0 equal to pi by 2. We can then write U theta equal to Pe cos pi by 2 minus cos theta, that is given by Pe cos theta, that is equal to minus P dot E.
This expression can alternately be understood also from equation 2.29. We apply equation 2.29 to the present system of two charges plus Q and minus Q. The potential energy expression is given by the equation 2.33. Here, R1 and R2 denote the position vectors of plus Q and minus Q. Now, the potential difference between positions R1 and R2 equals the work done in bringing a unit positive charge against field from R2 to R1. The displacement parallel to the force is 2a cos theta. Thus, V, R1, minus V, R2, equals minus E cross 2a cos theta. We thus obtain the equation 2.34. We note that U dash, theta, differs from U, theta, by a quantity which is just a constant for a given dipole. Since a constant is insignificant for potential energy, we can drop the second term in equation 2.34, and it then reduces to equation 2.32. We can now understand why we took theta 0 equals pi by 2. In this case, the work done against the external field E in bringing plus Q and minus Q equal and opposite and cancel out, so Q, V, R1, minus V, R2, equals 0. Electrostatics of conductors. Conductors contain mobile charge carriers. In metallic conductors, these charge carriers are electrons. In a metal, the outer, valence, electrons part away from their atoms and are free to move. These electrons are free within the metal but not free to leave the metal. The free electrons form a kind of gas. They collide with each other and with the ions, and move randomly in different directions. In an external electric field, they drift against the direction of the field. The positive ions made up of the nuclei and the bound electrons remain held in their fixed positions. In electrolytic conductors, the charge carriers are both positive and negative ions, but the situation in this case is more involved. The movement of the charge carriers is affected both by the external electric field as also by the so-called chemical forces. We shall restrict our discussion to metallic solid conductors. 1. Inside a conductor, electrostatic field is 0. Consider a conductor, neutral or charged. There may also be an external electrostatic field. In the static situation, when there is no current inside or on the surface of the conductor, the electric field is 0 everywhere inside the conductor. This fact can be taken as the defining property of a conductor. A conductor has free electrons. As long as electric field is not 0, the free charge carriers would experience force and drift. In the static situation, the free charges have so distributed themselves that the electric field is 0 everywhere inside. Electrostatic field is 0 inside a conductor. 2. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. If E were not normal to the surface, it would have some non-zero component along the surface. Free charges on the surface of the conductor would then experience force and move. In the static situation, therefore, E should have no tangential component. Thus electrostatic field at the surface of a charged conductor must be normal to the surface at every point. For a conductor without any surface charge density, field is zero even at the surface. 3. The interior of a conductor can have no excess charge in the static situation. A neutral conductor has equal amounts of positive and negative charges in every small volume or surface element. When the conductor is charged, the excess charge can reside only on the surface in the static situation. This follows from the Gauss's law. Consider any arbitrary volume element V inside a conductor. On the closed surface S bounding the volume element V, electrostatic field is zero. Thus the total electric flux through S is zero. Hence, by Gauss's law, there is no net charge enclosed by S, but the surface S can be made as small as you like, i.e., the volume V can be made vanishingly small. This means there is no net charge at any point inside the conductor, and any excess charge must reside at the surface. 4. Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside, on its surface. This follows from results 1 and 2 above. Since E equals 0 inside the conductor and has no tangential component on the surface, no work is done in moving a small test charge within the conductor and on its surface. That is, there is no potential difference between any 2 points inside or on the surface of the conductor. Hence, the result, if the conductor is charged, electric field normal to the surface exists. This means potential will be different for the surface and a point just outside the surface. In a system of conductors of arbitrary size, shape and charge configuration, each conductor is characterized by a constant value of potential, but this constant may differ from one conductor to the other. Electric field at the surface of a charged conductor E is given by the equation 2.35, where sigma is the surface charge density and n cap is a unit vector normal to the surface in the outward direction. To derive the result, choose a pillbox, a short cylinder, as the Gaussian surface about any point P on the surface, as shown in figure 2.17. The pillbox is partly inside and partly outside the surface of the conductor. It has a small area of cross-section delta S and negligible height. Just inside the surface, the electrostatic field is zero. Just outside, the field is normal to the surface with magnitude E. Thus, the contribution to the total flux through the pillbox comes only from the outside, circular, cross-section of the pillbox. This equals plus or minus E delta S, positive for sigma greater than 0, negative for sigma less than 0. Since over the small area delta S, E may be considered constant and E and delta S are parallel or antiparallel. The charge enclosed by the pillbox is sigma delta S. By Gauss's law, E is given by the equation 2.36. Including the fact that electric field is normal to the surface, we get the vector relation, equation, 2.35, which is true for both signs of sigma. For sigma greater than 0, electric field is normal to the surface outward. For sigma less than 0, electric field is normal to the surface inward. Electrostatic shielding. Consider a conductor with a cavity, with no charges inside the cavity. A remarkable result is that the electric field inside the cavity is zero, whatever be the size and shape of the cavity and whatever be the charge on the conductor and the external fields in which it might be placed. We have proved a simple case of this result already. The electric field inside a charged spherical shell is zero. The proof of the result for the shell makes use of the spherical symmetry of the shell. But the vanishing of electric field in the charge-free cavity of a conductor is, as mentioned above, a very general result. A related result is that even if the conductor is charged or charges are induced on a neutral conductor by an external field, all charges reside only on the outer surface of a conductor with cavity. The proofs of the results noted in figure 2.18 are omitted here, but we note their important implication. Whatever be the charge and field configuration outside, any cavity in a conductor remains shielded from outside electric influence. The field inside the cavity is always zero. This is known as electrostatic shielding. The effect can be made use of in protecting sensitive instruments from outside electrical influence. Figure 2.19 gives a summary of the important electrostatic properties of a conductor. Dielectrics and polarization. Dielectrics are non-conducting substances. In contrast to conductors, they have no or negligible number of charge carriers. Recall from section 2.9 what happens when a conductor is placed in an external electric field. The free charge carriers move and charge distribution in the conductor adjusts itself in such a way that the electric field due to induced charges opposes the external field within the conductor. This happens until, in the static situation, the two fields cancel each other and the net electrostatic field in the conductor is zero. In a dielectric, this free movement of charges is not possible. It turns out that the external field induces dipole moment by stretching or reorienting molecules of the dielectric. The collective effect of all the molecular dipole moments is net charges on the surface of the dielectric which produce a field that opposes the external field. Unlike in a conductor, however, the opposing field so induced does not exactly cancel the external field. It only reduces it. The extent of the effect depends on the nature of the dielectric. To understand the effect, we need to look at the charge distribution of a dielectric at the molecular level. The molecules of a substance may be polar or non-polar. In a non-polar molecule, the centers of positive and negative charges coincide. The molecule then has no permanent, or intrinsic, dipole moment. Examples of non-polar molecules are oxygen, O2, and hydrogen, H2, molecules which, because of their symmetry, have no dipole moment. On the other hand, a polar molecule is one in which the centers of positive and negative charges are separated, even when there is no external field. Such molecules have a permanent dipole moment. An ionic molecule such as HCl or a molecule of water, H2O, are examples of polar molecules. In an external electric field, the positive and negative charges of a non-polar molecule are displaced in opposite directions. The displacement stops when the external force on the constituent charges of the molecule is balanced by the restoring force, due to internal fields in the molecule. The non-polar molecule thus develops an induced dipole moment. The dielectric is said to be polarized by the external field. We consider only the simple situation when the induced dipole moment is in the direction of the field and is proportional to the field strength. Substances for which this assumption is true are called linear isotropic dielectrics. The induced dipole moments of different molecules add up, giving a net dipole moment of the dielectric in the presence of the external field. A dielectric with polar molecules also develops a net dipole moment in an external field, but for a different reason. In the absence of any external field, the different permanent dipoles are oriented randomly due to thermal agitation, so the total dipole moment is zero. When an external field is applied, the individual dipole moments tend to align with the field. When summed over all the molecules, there is then a net dipole moment in the direction of the external field, that is, the dielectric is polarized. The extent of polarization depends on the relative strength of two mutually opposite factors. The dipole potential energy in the external field tending to align the dipoles with the field and thermal energy tending to disrupt the alignment. There may be, in addition, the induced dipole moment effect as for non-polar molecules, but generally the alignment effect is more important for polar molecules. Thus in either case, whether polar or non-polar, a dielectric develops a net dipole moment in the presence of an external field. The dipole moment per unit volume is called polarization and is denoted by P for linear isotropic dielectrics. P equals epsilon naught Xi equation, 2.37, where Xi is a constant characteristic of the dielectric and is known as the electric susceptibility of the dielectric medium. The question is, how does the polarized dielectric modify the original external field inside it? Let us consider, for simplicity, a rectangular dielectric slab placed in a uniform external field E0 parallel to two of its faces. The field causes a uniform polarization P of the dielectric. Thus every volume element delta V of the slab has a dipole moment P delta V in the direction of the field. The volume element delta V is macroscopically small but contains a very large number of molecular dipoles. Anywhere inside the dielectric, the volume element delta V has no net charge, though it has net dipole moment. This is because the positive charge of one dipole sits close to the negative charge of the adjacent dipole. However, at the surfaces of the dielectric normal to the electric field, there is evidently a net charge density. As seen in figure 2.23, the positive ends of the dipoles remain unneutralized at the right surface and the negative ends at the left surface. The unbalanced charges are the induced charges due to the external field. Thus, the polarized dielectric is equivalent to two charged surfaces with induced surface charge densities, say sigma p and minus sigma p. Clearly, the field produced by these surface charges opposes the external field. The total field in the dielectric is, thereby, reduced from the case when no dielectric is present. We should note that the surface charge density plus or minus sigma p arises from bound charges, not free charges, in the dielectric. Capacitors and capacitance. A capacitor is a system of two conductors separated by an insulator, figure 2.24. The conductors have charges, say Q1 and Q2, and potentials V1 and V2. Usually, in practice, the two conductors have charges Q and minus Q, with potential difference V equals V1 V2 between them. We shall consider only this kind of charge configuration of the capacitor. Even a single conductor can be used as a capacitor by assuming the other at infinity. The conductors may be so charged by connecting them to the two terminals of a battery. Q is called the charge of the capacitor, though this, in fact, is the charge on one of the conductors. The total charge of the capacitor is zero. The electric field in the region between the conductors is proportional to the charge Q, that is, if the charge on the capacitor is doubled, the electric field will also be doubled at every point. Now, potential difference V is the work done per unit positive charge in taking a small test charge from the conductor 2:1 against the field. Consequently, V is also proportional to Q, and the ratio Q by V is a constant. C equals Q by V. The constant C is called the capacitance of the capacitor. C is independent of Q or V, as stated above. The capacitance C depends only on the geometrical configuration, shape, size, separation, of the system of two conductors. As we shall see later, it also depends on the nature of the insulator, dielectric, separating the two conductors. The SI unit of capacitance is 1 farad, equals 1 coulomb volt power minus 1, or 1 F equals 1 CV power minus 1. A capacitor with fixed capacitance is symbolically shown as, while the one with variable capacitance is shown as. Equation 2.38 shows that for large C, V is small for a given Q. This means a capacitor with large capacitance can hold large amount of charge Q at a relatively small V. This is of practical importance. High potential difference implies strong electric field around the conductors. A strong electric field can ionize the surrounding air and accelerate the charges so produced to the oppositely charged plates, thereby neutralizing the charge on the capacitor plates, at least partly. In other words, the charge of the capacitor leaks away due to the reduction in insulating power of the intervening medium. The maximum electric field that a dielectric medium can withstand without breakdown of its insulating property is called its dielectric strength. For air it is about 3 times 10 power 6 Vm power minus 1. For a separation between conductors of the order of 1 centimeter or so, this field corresponds to a potential difference of 3 times 10 power 4 volt between the conductors. Thus, for a capacitor to store a large amount of charge without leaking, its capacitance should be high enough so that the potential difference and hence the electric field do not exceed the breakdown limits. Put differently, there is a limit to the amount of charge that can be stored on a given capacitor without significant leaking. In practice, a farad is a very big unit. The most common units are its submultiples. 1 microfarad equals 10-6 F, 1 nanofarad equals 10 power minus 9 F, 1 pico-F equals 10 power minus 12 F. Besides its use in storing charge, a capacitor is a key element of most AC circuits with important functions, as described in Chapter 7. The parallel plate capacitor. A parallel plate capacitor consists of two large plane parallel conducting plates separated by a small distance, figure 2.25. We first take the intervening medium between the plates to be vacuum. Let A be the area of each plate and D the separation between them. The two plates have charges Q and minus Q. Since D is much smaller than the linear dimension of the plates, D2 very much lesser than A, we can use the result on electric field by an infinite plane sheet of uniform surface charge density, section 1.15. Plate 1 has surface charge density sigma equals Q by A and plate 2 has a surface charge density minus sigma. Using equation 1.33, the electric field in different regions is, for the outer region 1, region above the plate 1, E is given by 2.39. For outer region 2, region below the plate 2, E is given by the equation 2.40. In the inner region between the plates 1 and 2, the electric fields due to the two charged plates add up, giving the equation 2.41. The direction of electric field is from the positive to the negative plate. Thus, the electric field is localized between the two plates and is uniform throughout. For plates with finite area, this will not be true near the outer boundaries of the plates. The field lines bend outward at the edges, an effect called fringing of the field. By the same token, sigma will not be strictly uniform on the entire plate. E and sigma are related by equation 2.35. However, for d square very much less than a, these effects can be ignored in the regions sufficiently far from the edges, and the field there is given by equation 2.41. Now for uniform electric field, potential difference is simply the electric field times the distance between the plates, which is given by the equation 2.42. The capacitance C of the parallel plate capacitor is then given by the equation 2.43, which depends only on the geometry of the system. For typical values like A equals 1 meter square and D equals 1 millimeter, we get the value of C as given by the equation 2.44. You can check that if 1F equals 1 CV power minus 1. This shows that 1F is too big a unit in practice, as remarked earlier. Another way of seeing the bigness of 1F is to calculate the area of the plates needed to have C equals 1F for a separation of, say, 1 centimeter. The area is 10 power 9 square meter, which is a plate about 30 kilometers in length and breadth. Effect of dielectric on capacitance. With the understanding of the behavior of dielectrics in an external field developed in section 2.10, let us see how the capacitance of a parallel plate capacitor is modified when a dielectric is present. As before, we have two large plates, each of area A, separated by a distance d. The charge on the plates is plus or minus Q, corresponding to the charge density plus or minus sigma, with sigma equals Q by A. When there is vacuum between the plates, then E naught is given by sigma by epsilon naught.
And the potential difference V naught is given by V naught equal to epsilon naught d. The capacitance C naught in this case is given by C naught equal to Q by V naught, that's equal to epsilon naught A by d. Consider next a dielectric inserted between the plates fully occupying the intervening region. The dielectric is polarized by the field, and as explained in section 2.10, the effect is equal to two charged sheets at the surfaces of the dielectric normal to the field, with surface charge density sigma p and minus sigma p. The electric field in the dielectric then corresponds to the case when the net surface charge density on the plate is plus or minus sigma p. That is, the expression for E is given by E equal to sigma minus sigma p by epsilon naught, so that the potential difference across the plates is E equal to ED. That's given by sigma minus sigma p d by epsilon naught. For linear dielectrics, we expect sigma p to be proportional to E naught, that is, up to sigma. Thus, sigma minus sigma p is proportional to sigma, and we can write sigma minus sigma p equal to sigma by k. The k is a constant characteristic of the dielectric. Clearly, k is greater than 1. So we have V equal to sigma d by epsilon naught k. That's given by Qd by epsilon naught a k. The capacitance C, if dielectric between the plates, is then given by C equal to Q by V. That's given by epsilon naught a k by d. The product epsilon naught k is called the permittivity of the medium and is denoted by letter epsilon. So epsilon is equal to epsilon naught k. For vacuum, k will be equal to 1 and epsilon is equal to epsilon naught, where this epsilon naught is called the permittivity of the vacuum. The dimensionless ratio k is given by epsilon naught, and this is called the dielectric constant of a substance. As remarked before, from the equation 2.49, it is clear that k is greater than 1. From equations 2.46 and 2.51, k is done by C naught. Thus, the dielectric constant of a substance is a factor which is greater than 1, by which the capacitance increases from its vacuum value when the dielectric is inserted fully between the plates of a capacitor.
Though we arrive at equation 2.54, for the case of a parallel plate capacitor, it holds good for any type of capacitor and can, in fact, be viewed in general as a definition of the dielectric constant of a substance. Combination of capacitors. We can combine several capacitors of capacitance C1, C2, Cn to obtain a system with some effective capacitance C. The effective capacitance depends on the way the individual capacitors are combined. Two simple possibilities are discussed below. 1. Capacitors in series. Figure 2.26 shows capacitors C1 and C2 combined in series. The left plate of C1 and the right plate of C2 are connected to two terminals of a battery and have charges Q and -Q, respectively. It then follows that the right plate of C1 has charge -Q and the left plate of C2 has charge Q. If this was not so, the net charge on each capacitor would not be zero. This would result in an electric field in the conductor connecting C1 and C2. Charge would flow until the net charge on both C1 and C2 is zero and there is no electric field in the conductor connecting C1 and C2. Thus, in the series combination, charges on the two plates, plus or minus Q, are the same on each capacitor.
The total potential drop V across the combination is the sum of the potential drops V1 and V2 across C1 and C2 respectively. So the potential drop V is given by the sum of potential drop across the individual capacitors. That is V is equal to V1 plus V2, that's given by Q by C1 plus Q by C2. That is V by Q is equal to 1 by C1 plus 1 by C2. Now we can regard the combination as an effective capacitor with charge Q and potential difference V. The effective capacitance of the combination is given by 3 is equal to Q by V. Now comparing the equations 2.57 and 2.56, we obtain 1 by C is equal to 1 by C1 plus 1 by C2. This proof clearly goes true for any number of capacitors arranged in a similar way. The equation 2.55 for n number of capacitors arranged in series generalizes to V is equal to V1 plus V2 and so on up to Vn. Just given by Q by C1 plus Q by C2 and so on up to Q by Cn. Following the same steps as for the case of two capacitors, we get the general formula for effective capacitance of a series combination of n capacitors as 1 by C is equal to 1 by C1 plus 1 by C2 plus and so on up to 1 by Cn. Now we can consider the second case in which the capacitors are connected in parallel. Figure 2.28a shows two capacitors arranged in parallel. In this case, the same potential difference is applied across both the capacitors, but the plate charges plus or minus Q1 on capacitor 1 and plate charges plus or minus Q2 on the capacitor 2 are not necessarily the same. So Q1 is given by C1V and Q2 equal to C2V. The equivalent capacitor is one with charge Q is equal to Q1 plus Q2 and the potential difference V. So the charge Q is given by CV, that's equal to C1V plus C2V. The effective capacitance C is obtained from the equation 2.63. So C is given by C1 plus C2. That is the sum of the capacitors C1 and C2. The general formula for effective capacitance C for a parallel combination of n capacitors, which is given in figure 2.28b, follows similarly, where Q is given by Q1 plus Q2 and so on up to Qn. That is Cv is equal to C1V plus C2V and so on up to Cnv, which gives C is equal to C1 plus C2 and so on up to Cn.
Energy stored in a capacitor. A capacitor, as we have seen above, is a system of two conductors with charge Q and minus Q. To determine the energy stored in this configuration, consider initially two uncharged conductors 1 and 2. Imagine next a process of transferring charge from conductor 2 to conductor 1 bit by bit. So
that at the end, conductor 1 gets charge Q by charge conservation. The conductor 2 has a charge minus Q at the end, which is given by the figure 2.30. In transferring positive charge from conductor 2 to conductor 1, work will be done externally, since at any stage conductor 1 is at a higher potential than conductor 2. To calculate the total work done, we first calculate the work done in a smaller step involving transfer of an infinitesimal, that is vanishingly small amount of charge. Consider the intermediate situation when the conductors 1 and 2 have charges Q dash and minus Q dash respectively. At this stage, the potential difference V dash between conductors 1 to 2 is Q dash by C, where C is the capacitance of the system. Next, imagine that a small charge delta Q dash is transferred from the conductor 2 to 1. Work done in this step delta W resulting in charge Q dash on conductor 1 increasing to Q dash plus delta Q dash is given by delta W equal to V dash delta Q dash, that's given by Q dash by C into delta Q dash. Integrating the equation 2.68, we get W equal to integral 0 to Q dash delta Q dash by C, and that's given by 1 by C, Q dash squared by 2, the integration limits between 0 to Q. That's given by Q squared by 2C. We can write the final result in different ways. So W is given by Q squared by 2C, that's equal to half CV squared, and that's given by half QV. Since electrostatic force is conservative, this work is stored in the form of potential energy of the system. For the same reason, the final result for potential energy, which is given by equation 2.69, is independent of the manner in which the charge configuration of the capacitor is built up. When the capacitor discharges, this stored up energy is released. It is possible to view the potential energy of the capacitor as stored in the electric field between the plates. To see this, consider for simplicity a parallel plate capacitor of area A of each plate and separation is given by D between the plates. So the energy stored in the capacitor is given by half Q squared by C, and that's given by A sigma whole squared by 2 into D by epsilon naught A. The surface charge since the sigma is related to the electric field E between the plates. So the electric field is given by E equal to sigma by epsilon naught. From the equations 2.70 and 2.71, we get energy stored in the capacitor as U equal to half epsilon naught E square into AD.
Note that AD is the volume of the region between the plates, where electric field alone exists. If we define energy density as energy stored per unit volume of space, equation 2.72 shows that energy density of electric field, U equals half epsilon naught E square. Though we derived equation 2.73 for the case of a parallel plate capacitor, the result on energy density of an electric field is, in fact, very general and holds true for electric field due to any configuration of charges.